Okay, I'm recording now. All right, so if you're watching the recording, we are just computing the Laplacian of a rotationally symmetric solution V of R. Okay, so what have we done? So the Laplacian of U, right? It's just the sum of the second derivatives acting on V of R. We applied the chain rule here to take the first derivative. We have computed dr dxi now, which is xi over r. Okay, and so if I plug this in now, I get dxi xi over r v prime of r. Okay. And then I can go further now by saying, well, now let me take that second derivative, and I'm going to get the sum from I equals 1 up to n of 1 over r. So just sort of use the product rule twice on this, v prime of r plus xi v prime of r dxi of 1 over r. We'll compute that in a minute. Xi over r now v prime prime of r dr dxi. Okay, so just a bit of multivariate differentiation. Okay, so what does this come out to be? Well, the next line, we just get this term coming along for the ride, right? V prime of r over r minus now xi squared over r cubed, okay, v prime of r plus now xi squared over r squared v prime prime of r. Okay, so I can factor out I won't do that yet. Okay, so I can rewrite this as 1 over r squared now, and notice that this is a sum, right? So I can pull the 1 over r squared out of the sum. I can pull the v prime prime out of the sum, right? And then I just have I equals 1 up to n x I squared v prime prime of r. So just a bit of rearrangement. This term, right, I just pulled these two terms out of the sum, but notice that this is going to be r squared here, so those will cancel out. So I get a simplification from that. This term here, right, if I pull these both out of the sum, I'm just gonna have n over r v prime of r. And then this term here, if I pull everything out, I'm just going to have, again, a factor of r squared coming from this, and then n xj squared. Sorry, I'm squeezing things in here. I'm going to drop this down to the next line. Okay, so minus 1 over r cubed, the sum from j equals 1 up to n xj squared v prime. Okay. All right. So again, this thing's going to be just r squared here, right? This is, we're going to get a cancellation here. We get down to just a factor of 1, right? So if I write all this out, I'm going to switch to the next slide now. Is that all right? Okay. I'm going to get that the Laplacian of u is equal to v prime prime plus n minus 1 over r v prime is equal to 0, right? Because the Laplacian of u is equal to 0. Okay. this is just an ODE now. So how do I solve this? Well, I can divide through by v prime, and I get v prime prime over v prime is equal to minus n minus 1 over r. Okay, so if I integrate this up, then I get the log of v prime differentiated, right, would give me this. This is equal to minus n minus 1 over r. If I integrate that equation up, I get the log of v prime is equal to minus n minus 1 log of r plus a constant, okay? If I exponentiate now, I get v prime is equal to just a, some constant over r n minus 1, right? Where I've just taken a is equal to e to the c. And I get v of r is equal to, now there's a couple different cases, right? And remember, n is an integer here, right? So what can happen here? So a over r to the n minus 2 plus b if n is greater than or equal to 3, and it's going to be a log r plus b if n is equal to 2, okay? And we won't worry about that n equals 1 case because we wouldn't have had to even go through this whole process for the n equals 1 case. That's just going to be a linear function in that case, okay? So a and b we can take to be free constants, okay? Now we'll normalize to get the fundamental solution, just like we did in the case of the heat equation. And in that case, we have phi of x is equal to what? Well, I'm going to write this out. So 1 over n minus 2, something I'll call alpha n, which I'll define in a minute. Although I think I maybe defined it a few lectures ago when we were talking about heat equation. N greater than or equal to 3. And then minus 1 over 2 pi log x for n equals 2. And so what happened to the constants? Well, if I want this thing to be integrable over over Rn, then I can't have a constant because then the integral would blow up. So I have to drop the constants because of that. So where is this defined? It's defined where everywhere on Rn, except, of course, as you expect, where we get this singularity at the origin, right? So just like the heat equation had this singularity at the origin, we get it here, right? You can think of this as sort of a kernel that we can sort of convolve, we'll be able to convolve things with in order to get solutions to boundary value problems and Poisson's equation, which is sort of the inhomogeneous version, okay? Alpha n, let me define in a minute here. Alpha n, I'll go ahead, is equal to the volume of the unit sphere, okay? S n minus 1 in Rn, okay? So for instance, alpha 2 is equal to pi, alpha of 3 is equal to 4/3, right, pi r cubed, r is 1 for the unit sphere. Alpha n in general is equal to lambda, pi n to the n over 2, gamma function of n over 2 plus 1. And what's the gamma function? Gamma of z equals integral from 0 to infinity s to the z minus 1 e to the minus s ds, okay? Gamma function, okay? And let me just make one remark now. okay, before I catch a breath, about the fundamental solution, okay? As I remarked on, right, so phi of x is singular, right? Because if I plug in 0 here, I get blow up. But it's integrable on bounded sets, okay? And Laplacian of phi is singular and not integrable on bounded sets containing the origin, okay? So we'll see what considerations we have to deal with when we start introducing this as a fundamental solution that we're going to convolve against, okay? So like I said, I think the best kind of hand-wavy way to think about this is that singularity essentially is going to help us extract properties of the solution that will allow, sort of a general solution to line up with inhomogeneities and boundary conditions. Okay, just like the delta function that you get in the case of the heat equation allows you to recover the initial condition when you convolve against it. Okay. Questions about this? Okay. So yeah, I like to show that. I mean, it's kind of a fun calculation. The idea of using a rotationally symmetric assumption in order to reduce a PDE to like a solvable ODE, that's not just helpful in the case of Laplacian. That's an often used kind of trick in applied math problems. If you have some kind of symmetry in your problem, you can massively reduce the dimension of your problem and often make it solvable, and then use kind of asymptotic methods to say, well, what happens if I start to introduce asymmetry or something like that? Okay. So what's this fundamental solution good for?